Hey class, when we last met in person, we were working on gas laws. I believe we had just finished a gizmo, a little online lab investigating the gas laws. And we wanted to go through this graphing worksheet. Since you're going to be evaluated on recognizing the correct graphs for the different gas laws and identifying which gas law is represented in which graph, I think this is something we should go over. You all should have this if you were there the last day. If not, you can print out a copy of it. It'll be linked in this assignment for you to print out. And then, of course, there is a little quiz homework to follow where you have to answer questions regarding what we've learned today. Hopefully what we'll learn today is how to identify and draw the different graphs for the three gas laws: Boyle's law, Charles' law, and Gay-Lussac's law, and how to identify what values go on which sides, what shape a graph is, and whether some axes are correct or unnecessary. Now this first one, this is volume and temperature, and we need to read the units. Volume units, they don't give it to you. And if you recall from solving gas law problems, the volume unit doesn't matter. What matters is it's consistent. The temperature unit does matter. Now this is in Kelvin. So the first thing we note is that the lowest Kelvin can be is 0. So this whole left side of that axis is irrelevant and incorrect. And same is true for the volume. You cannot have less than 0 volume, so this whole negative y-axis is invalid. We should only be graphing in this first quadrant. And the relationship that is volume and temperature, that is Charles' law. Charles's law, which says that volume 1 and temperature 1, their ratio is constant. So that means a constant slope. So at any other place, we could find the, that's a 2, the temperature given a specific volume. So they have a constant ratio, that's a constant slope. So what we get is a graph like this. What that slope is depends on the gas, and the pressure depends on the pressure, but the pressure's got to be constant. So that is the way Charles' law works. And what that says is that if volume goes up, then temperature must go up for constant pressure. Have to have a constant pressure for this. So there you go. Volume and temperature are directly related. We could write that down too. They're directly related. Okay, that's our first graph, Charles' law. Now this next graph here. All right, temperature, we got to worry about units. That's in Kelvin. Lowest it can be is 0. That's good. Doesn't have any mass. Lowest that can be is 0. But this is not a gas law. There is no relationship between temperature and mass. Raising the temperature of a gas does not increase its mass. So these things are not related. Mass is independent of temperature, and temperature is independent of mass. So for a sample of gas, if you have a certain mass, it doesn't matter what the temperature is, you're going to have that same mass the whole time. And likewise, if you have a certain temperature, you could have all kinds of different masses. If you maintain that temperature, the adding more mass does not mean you add more temperature. So these are unrelated, not a gas law. Not a gas law. These are unrelated. So we don't got to worry about that graph at all. If you see a temperature mass graph on a test as a choice, not the right choice. Then we have pressure and volume. So this is Boyle's law. Actually, I heard a story that it actually, Boyle isn't the guy who discovered it. So he's just the guy who got credit for it, for publishing it under his name, but it was actually somebody else. You'll have to look that up on Wikipedia or something about who actually established the relationship between pressure and volume for a constant temperature. Now the ways this works is, well, first let's check those axes. Pressure can be in any unit as long as the unit's consistent, so that's fine. Volume can be in any unit as long as we're consistent, that's good. You can't have less than 0 volume, so this axis is incorrect. You can't have less than 0 pressure. Yeah, overall, absolute pressure can't be less than 0. You can have a pressure differential, a gauge pressure, maybe, of less than 0 if it's going the other way. But the absolute pressure cannot be less than 0. So that's not going to make sense. So we can get rid of those two axes. Now, how do these relate? And here we know as you squeeze something, it gets smaller. So higher pressure gives you lower volume. The equation turns out to be pressure 1 times volume 1. That ratio, that product rather, is always a constant. Pressure 2, volume 2. So when the product is a constant, that gives you an inverse relationship. Pressure is inversely related to volume. So as P goes up, V goes down. And this is, of course, for a constant temperature. Constant temperature. So what's this graph look like? Well, this is going to be a curve that's going to asymptote. It's called a hyperbola. That comes down and over. They technically never reach 0. You can never quite get to 0 volume if you have some mass of gas in there, and you can never quite get to 0 pressure unless you have no gas. So that's the way that looks, Boyle's law. Now you could make that into a straight line. You could graph this. You could do pressure versus 1 over the volume, the inverse of the volume, and that would give you a straight line. Since this curve indicates an inverse relationship between the y and the x-axis, if we graph the y versus the inverse of that x, we'd get a straight line. So that might show up on a trickier question. Okay, we've got to go on to the next one. Okay, here's our next graph. We've got pressure and temperature. Now, pressure and temperature is the Gay-Lussac's law. That's that one. And that says that the ratio of pressure to temperature is constant. So we might recall previously from Charles' law, when we have ratios that are constant, that means the slope's constant. That's a direct relationship. That's going to be a straight line. So we know this is going to be a straight line now, but we be careful with our axes. Pressure can be any unit, just has to be consistent, but cannot be negative. So temperature, we've got two units we work with, Kelvin and Celsius. Kelvin, 0 is the smallest, but Celsius, negative 273 is the smallest that it can be, the lowest temperature. Not really small, but low. So this is a direct relationship. Pressure is directly related to temperature. right? The hotter something gets, the more it pushes out. If you heat a balloon, you might have to do this next week. If you heat a balloon up, it's going to get bigger. If you put a balloon in the freezer, it's going to get smaller. We'll see if you have balloons. So how does this graph look then? Well, it's got to be a direct relationship. That's a straight line, constant slope, but it's going to hit 0 pressure when the temperature is negative 273. So it'll be something like this. Oops, long. So we get a straight line indicating a direct relationship. However, the minimum temperature is negative 273 when we hit minimum pressure of 0. So as the pressure goes up, the temperature will go up. And again, this will all be for constant volume. For constant volume. All right, our next graph. Now here's a temperature and volume again. This is a Charles' law again. Our axes are flipped. That doesn't really matter much, but we got to be careful of those axes. So that's Charles again, where V1 over T1 equal V2 over T2. Then you can copy down all the stuff from the other side. They're directly related for a constant pressure. Now here's the deal though, on this axis we're in Celsius, so we can go down to negative. Volume cannot be negative, so that's not going to happen. So this graph ends up looking like this. It should be a direct relationship, so that means it's a straight line, constant ratio, constant slope. And we have to just be careful that when we have a Celsius in the temperature, the minimum is a negative 273. No other axes in these gas laws, volumes, pressure, or Kelvin temperature, can be negative. Right? Volume goes up, temperature goes up, directly related. Is what they are. And here we have temperature in Celsius and pressure. So pressure can't be below 0. Get rid of that. Temperature when it's in Celsius can go down here. Now this is Gay-Lussac again. Where we've got P1 over T1. The ratio of the pressure and temperature is constant. So ratios relate to slopes with graphs. So the slope is constant, so that's a direct relationship. And again, can't have a negative pressure. Celsius does have negative temperatures, and the minimum is 273. So it's going to look, boom, like that. It looks a lot like the Charles' law graph. And again, as pressure goes up, the temperature will go up, and they're directly related. And again, that'd be for a constant volume. Okay, so you need to know each of these graphs, what you need to be able to say this graph belongs to that law, or you need to be given a law and create the graph. You have to be able to tell me if it's a direct relationship with that graph or an inverse relationship with that graph. And there will be tricks thrown in with these negative axes that often do not belong. Okay, hope that's helpful.